Right, another technique for solving a quadratic is to complete the square. And we'll talk about what that means exactly, but first, I think it'll be helpful to look at a couple of introductory examples here. So let's say I want to solve this equation, x squared minus 7 equals 0. Because there's no x term, one way we could do it is to add 7 to both sides. Then we get x squared is equal to 7. And if I know what x squared is equal to, I can solve by taking the square root on both sides. Now, here's an important note. When we are the ones imposing the radical on the equation, like the radical sign was not a part of it to begin with, when we are taking the square root, we have to consider both the positive and negative roots. And so this gives us two solutions, x equals the square root of 7 or negative square root of 7, and we usually write that just by saying plus or minus the square root of 7. Certainly you could write them out separately, right? We could say x is root 7 or x is negative root 7. It's either way to express the answer is fine. Now, let's do another one here. X minus 3 in parentheses squared is equal to 16. Now, this is actually remarkably similar to part A. The difference is, of course, in part B, we're squaring not just x, but the expression x minus 3. But the same technique can work. You know, let's take the square root on both sides. I have to make sure on the right side that I'm taking both the positive and negative square root, that I consider both of those. So this gives us two equations that results from this. This gives us x minus 3 equals 4. Or x minus 3 equals negative 4. And now we just add 3 to both sides for both of these equations to get our solutions. So we get x equals 7 or x equals negative 1. Now, what made this sort of square root technique work for these equations was that I had a perfect square, right, hanging out by itself on the left side. So up top it was just plain old x squared. In part B it was the square of x minus 3. So I had like a perfect square, which is where my variable lived, and then just a constant on the other side of the equation. So if we're looking at an equation in this form, we know how to solve that. We could take the square root on both sides. What we're going to do in this section is learn how to take any quadratic equation and write it in this form, and that process is what we call completing the square. We call it completing the square because we want to end up with a perfect square on one side of the equation. Now I've outlined our procedure here that we're going to follow, and I'm pretty much just going to go through it by example. You always want to start by having your x squared and x term together on one side and putting the constant by itself on the other side. And then also, item 2 here says divide both sides by the coefficient on x squared so that you have an equation in this form. The idea here, the point is that we can complete the square on 1x squared, not 5x squared or negative x squared. We need that coefficient on x squared to be a positive one. And if it's not starting out that way, we just get there by dividing both sides. I'm going to talk about the rest of those steps as we see it in an example. So this one, let's see, we start out with x squared plus 6x plus 5 equals 0. Now I want to get the constant by itself on the other side, so we're just going to subtract 5 from both sides. So we have x squared plus 6x equals minus 5. Now I'm going to leave some space on the left side Notice I've already got a 1x squared, so that is all taken care of. I'm leaving some space. This is sort of where the magic happens. I want the left side to be a perfect square. And the way that we're going to make that happen is you take a look at this coefficient, also include the sign, so I got a positive 6. Now what you want to do is cut that in half to get you 3, and then square that, and that's what you're going to add to both sides of the equation. So we are going to add 3 squared to both sides. Now, some people like to just square it and say, oh, I'm going to add 9 to both sides, and obviously that's fine to do. 3 squared is equal to 9. I always write it this way because it's going to make my next step, I think, a little bit easier. The left side, after you've added that term, now we could add anything we want to both sides of an equation. We chose to add this term because we are terribly clever, and we know that if I add 3 squared to both sides, then this left side is a perfect square. Right? We're going to factor it. And this is what a perfect square looks like. It's some stuff squared. And what goes inside is the x and the 3. And that's a positive 3. So this is x plus 3. You can check, right? If you multiply out x plus 3 and x plus 3, you get x squared 3x, 3x, 9. So that's x squared plus 6x plus 9. And that's what we get here, right? That's what we have. So this is, in fact, how this factors. And on the right side, we got some arithmetic to do. Negative 5 plus 9 is 4. Now we're looking at an equation where the left side is the perfect square. That's where our x lives. And we have a constant by itself on the other side. We're ready to take the square root. We need to consider both the positive and negative roots of 4. And so we know that x plus 3 is plus or minus 2. And now all we need is to subtract 3. Now be careful here. I've written it this way, the plus or minus 2, right? I could have teased it out, separated it out into 2 equations. X plus 3 is 2, x plus 3 is minus 2, and solved each of these. It's pretty common to write it this way, so I just want to show you, if you're inclined to write it this way, to be careful, because sometimes people will say, oh, that's a plus or minus 1 or plus or minus 5, but the way that this plays out is we have negative 3 plus or minus 2. That means that I have negative 3 plus 2, which is negative 1, or negative 3 minus 2, which is negative 5. So these are our 2 solutions. All right, when you solve a quadratic by completing the square, if you get what I would call nice answers, meaning answers that are either integers or fractions, but basically this step here, right, when we took the square root, we were taking the square root of 4, that's a perfect square, like we didn't need to approximate anything, right? So when that happens and you get these sort of nice solutions, that's an indication that your quadratic would have factored in the first place. So you could actually solve that one by factoring, and maybe when you looked at it, you already saw that you could factor the x squared plus 6x plus 5. But not every quadratic will factor, and that is why we need more techniques, more than just factoring to help us solve. Let's take a look at this next example. So first of all, I need to get that constant by itself on the other side of the equation. So we will subtract 17. We get 2x squared minus 16x equals negative 17. And then we have a 2x squared. We need to complete the square on 1x squared, right? We want that coefficient on x squared to be positive 1. So I'm going to just divide both sides by 2, which really is the same as dividing each term by 2. So on the left side, we get x squared minus 16 over 2 is 8x. Now I'm going to leave some space for the magic, and we have minus 17 halves over here. Now we're ready to complete the square. So as before, I take a look at this coefficient, including the sign. So I got a -8. I'm going to cut that in half and square it. So I'm adding the square of -4. And, you know, the square of -4 is still positive 16. But I write it this way because it's going to help me, it's going to make my next step easier. The reason we added the square of -4, the reason we added that is because it completes the square. This left side is a perfect square. It is the square of, our first term is x, our next term is -4. So x minus 4. Let's see, we need to do some arithmetic here. So this is -17/2 plus 16. That's 16 over 1. Let's get a common denominator. So 32 minus 17 is 15. So 15/2 is the number over here. All right, now I've got a perfect square on the left side. That's where my x lives, and then a constant by itself. The next step is to take the square root on both sides. On the right, I've got a plus or minus. So here's where this leaves us. Now, on the left side, we're taking the square root of a perfect square, so we get x minus 4. On the other side, we have plus or minus the square root of 15/2. And the only thing left to do to solve is to add 4 to both sides. So now we get 4 plus or minus the square root of 15/2. So our two solutions are 4 plus 15/2 or 4 minus 15/2. You could leave it in this form if you like. I don't take issue with that. You can also get it in, kind of simplify the radical, rationalize denominators, which we're going to do in a minute. But I just want to point out that when we solved, right, I ended up with this radical that wasn't a perfect square. So if my choices are either to approximate or to keep the radical. And in a situation like this, what that means is that the original quadratic, that is, we could not factor that. It is what we call irreducible. It's kind of like a prime, right? That won't factor. And so completing the square was our path to solving this, since it's an equation, since that quadratic would not factor. Now, you could, if we want to simplify here, the first step would be, let's split up that radical over division. And then we'll rationalize this denominator. So times root 2 times root 2. So we get 4 plus or minus the square root of 30 over 2. And, as I said before, you could leave it in this form, or you could rationalize. Either's okay. If you were asked to write the answer in an exact form, you should write it in one of these two forms. If it doesn't specify, or if you're solving a quadratic to help you solve a problem and it makes sense to approximate, you can also just approximate. Speaking of word problems, let's do one. Here we've got a skier that rides up a chairlift and then skis down. So we're kind of have a simplifying assumption here that it really is just the same distance up as it is down. So don't consider the fact that the skier might go off on a side trail or anything. Just think of a straight up and straight down trip. So we have the same distance up and down, and we know that it's a 1,200 meter trail. It takes her 8 minutes to go up and down, right? That's the total time. And they tell us that the skier averages 10 meters per second faster on the way down than on the way up. And we're going to find her average speed down the trail. So this is a problem. We've done ones like this before, right, that involves distances and rates and times. So there's more than one way, I suppose, that we could do this, but, so here's the basic, right, distance equals rate times time. I'm going to rearrange that to solve for time. So if you divide both sides by r, you get d over r is equal to t. And I'm going to focus on the fact that we have a total of 8 minutes. All right, so I'm going to make an equation that has this basic structure, that the time it takes to go up plus the time it takes to go down is equal to the total time. Now, each of these times is a distance over a rate. Distance over the rate going up plus the distance over the rate going down is equal to the total time. And we know the distance, right? They told us that it's a 1,200 meter trail. So we know what that is. Now we have these, so those, so we end up with 1,200 over the rate going up plus 1,200 over the rate going down. It looks like we've got these two variables, right? These two different rates. But they also tell us that the skier averages 10 meters per second faster on the way down than on the way up. So we can use that to write an expression. We're going to pick one of these to be our variable. So I'll say I'm going to let r equal to the rate going up. And then if she averages 10 meters per second faster on the way down, that means that the rate going down is r plus 10. Now if we rewrite our equation with this information, we have 1,200 over r plus 1,200 over r plus 10 is equal to 8 minutes. Now, it's a total of 8 minutes, and our rates are in meters per second. So 8 minutes, let's see how many seconds that is. So 8 times 60 is 480. So now here's an equation that models this problem. It's an equation with fractions. We know how to solve those. We're going to identify the LCD and then multiply both sides by that LCD. The LCD I think is pretty quick to recognize, pretty easy to recognize as being r times r plus 10, right? We need both of those factors to get everything to cancel. So let's multiply. Over on the right side, our first term, the r's cancel. The second term, the r plus 10s cancel. So we have 1,200 times r plus 10 plus 1,200 times r is equal to 480 r times r plus 10. And maybe by now we're recognizing and starting to see that a quadratic equation will result, right? I mean, our original equation, the equation that we wrote here that models the problem, that's this equation. That is itself not quadratic because we have r's in the bottom. But once we clear denominators, we will, we do end up with a quadratic equation. Let's expand these products. 1,200 r plus 12,000 plus 1,200 r equals 480 r squared plus 4,800 r. So there's, we could see now that we do in fact have a quadratic because of that r squared term. Let's see. So let's solve this. I want to get everything on one side except for the constant. I want the constant by itself. And I think maybe what I'll do is just start by combining these like terms here. So we got 2400r plus 12,000 equals 480r squared plus 4800r. Now I'm going to subtract 2400r from both sides. And, you know, I don't know about you, but I really like when I'm completing the square, I like having my r squared and r terms on the left side of the equation. So I'm going to take this part here, and I'm going to write it on the left side. So 480 r squared plus 2400r equals 12,000. Before we can complete the square, we need to divide out by the coefficient on r squared, so I'll divide by 480. So r squared plus 2400 divided by 480 is 5. I'm going to leave some space for the magic. And then 12,000 divided by 480 is 25. Now we're ready to complete the square. And we are going to be clever and choose a number to add to both sides. It'll give us a perfect square. Remember, we do that by taking this coefficient, cutting it in half, and squaring it. And adding that to both sides. So we're going to add the square of 5 halves. Now the left side here, that's a perfect square. That's what a perfect square looks like. We're going to grab the r and the positive 5 halves. So r plus 5 halves. And that's equal to, let's see, 25 plus 5 halves squared. Let's see, that's 25 over 4. Getting a common denominator. That would be, our denominator is 4. 100 plus 25 is 125. So we have completed the square. Now we're ready to go ahead and solve by taking the square root on both sides. We need to consider both the positive and negative root. I'm going to carry the square roots all the way through my calculations and then approximate at the end to get a result. You certainly could approximate at the beginning, right at this point, since we know being an application problem, we're going to want to approximate anyway. We get r plus 5 halves equals plus or minus. Now I'm going to split up this radical over division. So the square root of 125 over the square root of 4. And the square root of 4 is 2. Oops. And to solve for r, we're going to subtract 5 halves. So I've got minus 5 halves plus or minus the square root of 125 over 2. They already have a common denominator. That note the common denominator of 2. So we could write it as minus 5 plus or minus the square root of 125 over 2. And at this point, you know, I might just go ahead and approximate, but I would be remiss if I didn't mention that if we wanted to write it as a nice simplified radical, we can actually take, you know, 125 is 5 cubed. So you could rewrite that as -5 plus or minus 5 root 5 over 2. But now we're going to get our two solutions. Okay, so one solution we get by taking -5 plus the square root of 125 and then dividing by 2. So I'm going to make sure that's all in the numerator. -5 plus square root 125 divided by 2. We get 3.09. And the other solution is -5 minus the square root of 125 over 2, and that's a -8.09. Now, you know, when you think about this, you know, these numbers are coming up as solutions to this equation, but they're supposed to be solutions to this problem. So the skier is going up the, you know, up the chairlift and then skiing down, right? And R represents the rate going up. So the rate going up is not going to be a negative value, right? So the rates at which the skier is going, these are positive rates that the skier is traveling in. So we could just eliminate this, and that's often the case with a lot of problems, like applied problems that you might solve by modeling them with a quadratic equation, right? You get two solutions. Usually one of them we could throw up because it's just not feasible. So the rate going up is 3.09 meters per second, and then we want to make sure we answer the question. Find her average speed down the trail. So we're going to add 10 meters per second to that. .09 meters per second. Okay.